use this.
Okay. Sorry, let me make that easy for you. Beautiful.
And just já viste a versão?
Just, this will work.
Excuse me, can I? Or you still haven't?
Oh, is it? Sorry. Oh. So how do I?
Wait a minute, because I'm just trying to see if this doesn't. It's quite glitchy so
Oh.
far.
Sorry about that.
No. It's not your fault. It's the material's fault.
This Windows laptop don't have anything useful.
There we go.
So, why isn't this not full screen? Is this full screen? The projector seems inside. Is that me or?
Open the session and then you put it.
Yeah, go ahead.
So good morning, everyone. It's time to open the work for today. Welcome as well if you are online. We have a shorter day today, just until 12 o'clock here, local time, but it's a super interesting one. So we're going to talk about surrogate models and scientific informed machine learning, sometimes also mentioned called physics informed machine learning. Someone else, please.
All right, let me, a bit too tall here. Can you guys hear me? Whoops. Cool. All right, so first and foremost, my name is Enes Abdel-Rahim. I am a team lead at JuliaEO for the AI division, and I'd like to first and foremost extend my gratitude to the conference organizers for inviting me here, and for all the attendees as well. And I'm very excited today to talk about surrogate models. I've had the, really, to be honest, the pleasure to speak with so many different people here working on very, very hard problems. And I'm looking forward to going through this presentation to kind of give people an idea of what the future of modeling and simulation workflows could look like if we all kind of band together and understand the nature of artificial intelligence and how we can apply it to these workflows. And really, one of the interesting kind of sub-applications of this is surrogates. So we'll be going through what a surrogate is step by step. There's an agenda here. And the key thing that I want to mention about this presentation is, well, one, it could be prettier if the colors weren't dim. I'm not sure what's going on with the projector here. But really, the goal of this presentation is to have people walk away with a strong intuition of what a surrogate is, how do you build them, and how do you intuitively understand how they themselves learn from data. And so that when you go through your own workflows of building a surrogate, you have a strong intuition of what to do and what not to do. And this is really important because machine learning can be easy with just an API of just building anything, but having the right knowledge so that the thing that you build actually does what you want is key. I'm not sure if my voice is my voice coming in and out, or is it just me? Thank you. Okay, so that's the agenda for today. And I want to be very clear that this is more of an informal talk. I'm not going through much math. What I am doing instead is going through visualization examples that explain everything step by step. One thing I also want to mention is that this is more of an open forum, so I am welcoming questions, comments, or concerns throughout the presentation. Please do not be shy in any way, shape, or form. If you do not understand anything, stop me at any time and ask me questions. I'll be more than happy to kind of answer. Okay, so the first thing that I want to talk about is just the basic description of what a deep learning surrogate model is. And in particular, I want to make mention that the kind of surrogate models that I'll be talking about today are ones that are based on simulators. So if the source of your data comes from a simulator, this is what this talk will be about. And the reason why this distinction is important is because there's many different techniques depending on the context and scenario that you're in. But in our particular case, when you have a simulator, it becomes both easy and hard at the same time. And I kind of want to walk through that step by step. So the first thing I want to do is kind of introduce the very high level idea of what a deep learning surrogate is. And really I wanted to say a deep learning surrogate because there are many different machine learning techniques that allow you to generate a surrogate that has nothing to do with deep learning at all. And in particular, the reason why I want to focus on deep learning is because in general, these sets of algorithms scale very well with data. And that's a very important point when the scenario that you're in requires you to start with a simulator of some kind of physical system and then generate some kind of surrogate for it. But what is a surrogate? Well, simply put, you can understand a surrogate as a high-performance stand-in for your model. So if you're dealing with some kind of climate model or anything else that may take a very long time to simulate and you need something that is much faster or you need something that is differentiable, a surrogate model is a perfect fit for those kinds of scenarios. And we'll go through, later on in the slides, we have a series of examples, or rather scenarios in which when you should apply a surrogate, when you shouldn't apply a surrogate, and we'll go through these things very deeply. But on the right here, there's a very interesting diagram. It's a very basic neural network of only one layer. And this is more for visualization purposes, but what I want to kind of explain to everyone here is how a basic neural network learns and give you an intuition of this fact, because once you understand this idea, then it'll be easy for you to reason about what you need to do next whenever you're given some kind of problem or scenario. So this is a great diagram, and there's also a very great website that kind of intuitively explains this idea by Michael Nielsen. But as you can see, you just have a series of inputs. So in this case, in order to keep things visual and tangible for folks here, the idea is we're going to be working with very small input spaces and a single output just so that it's amenable to visualization. And then near the end of the presentation, we'll be going through a more sophisticated version of a surrogate, which is actually based on the hackathon challenge that will be on Friday, which I strongly recommend everyone to attend and join. Not only is the Rainmaker simulator one of the coolest things that I've ever used in the climate space, but the results for the surrogates will be very fascinating, and it'll give you guys a kind of perspective of what is possible once you kind of merge these different domains of science and engineering and artificial intelligence. Now, my talk is not really going into the direction of scientific machine learning. That will be the talk right after mine, which is Chris's. So this is more of like a black box approach. But the idea is, as a scientist, as an engineer, our biggest concern is that when we build these kinds of models and they're completely a black box, we have some concerns of how this thing will perform in regions where we might not have trained it. And the key idea here is to make sure that we have the right intuition to kind of navigate this difficult problem. So the idea is very simple. You have a neural network. It has a bunch of layers. It's represented as a matrix. Here it's only one layer. And you can see that if you just change one of the weights, what it effectively tries to do is it'll take your input space, so your x and y coordinates in this case, and it'll kind of almost like chop it up. And you can almost imagine that as it modifies the weights, it's just literally raising or lowering, in this visual example, what's called a tower cell. And this is purely for visualization, of course. A neural network technically does not have these kind of isolated groups of layers. But the key thing that I want to bring out here is that the way this particular model ends up learning is that it's very similar to kind of partitioning your space and then fitting different regions depending on where you have data. And this is going to be much more intuitive in the next couple of slides. But the one thing that I also want to mention about these classes of algorithms, especially for deep learning, is that they have a very specific, not very specific, but they have the property, or rather they have a universal approximation theorem. And usually this kind of theorem states that, given enough data and enough model complexity, and I'm paraphrasing here, you can represent any continuous function to any arbitrary degree of accuracy. And this is very, very important because what this means that if you set up the right scenario, you can learn any function regardless of how hard it is, how hard you think it is. Whether you understand the relationship or not, there exists a function, there exists a neural network with enough complexity and data that will learn that particular function. And this is really important because what this means is that if you have a really, really hard problem and you set up the data environment right and you set up the architecture right, you can come through with something that will actually solve what it is that you need. But the real trick here, and of course, in general with these kind of approximation theorems, is that all it says is that there exists an answer to your question. But how do you find that answer? How do you set up your environment, your data, your architecture, so that at the end of all that in the workflow, you actually come out with a neural network that will give you, that will represent your model or represent the function of interest. So what we're going to do together is we're going to go through a very, very, very basic example to help people understand some core ideas when it comes to surrogate modeling. So what we have here is we have a surface on the left-hand side, and it's just, you have two inputs. You have your x and y coordinates, so you can pick any point in space, and then it has a corresponding output, which in this case is the z coordinate. And the reason why we chose a lower dimension is so that everything can be visualized. And the key thing that I want to show here is that on the left-hand side, you see the real surface. In the middle, you see the samples that I've taken from it. And on the right-hand side, you can see a neural network that's randomly initialized. This is something that has not been trained before, right? So you can see that its actual shape and whatnot does not even represent the real surface, obviously, because it hasn't been trained. But this is the kind of starting point. And the interesting thing that I want to point is that the neural network has no knowledge of the real surface. This is a very important point. It has no knowledge of the real surface. It only has knowledge of what it can see, which is the points that you provide. So this is the kind of first point that I want to get through. So what we're going to do, and what I've done in the next kind of series of animations that will explain this process, is I've trained a one-layer neural network, but I've started off very small. And this is, the reason being is because I'd like to demonstrate a very, very important point when it comes to training these kinds of models. So what we're going to do is we're going to take this neural network that's on the right-hand side, and we're going to train it on the sample data. That's the first thing. And the network is going to be very, very small. So when we do that, can everyone see, for some reason, from my perspective, it looks dimmer than usual. Is that clear for people? Oh. Of course, yeah, sure. Yeah, sure.
No, I think it would probably not be here.
Yeah, I guess. Yeah, if it's not easily resolvable, I suppose we can continue. Yeah.
Try to change your screen resolution.
I'm not really sure how to do that.
Oh, okay. So,
Yeah, of course, please. It's okay. I think we can just keep going.
we call the technician anyway. So when you arrive, maybe it works. Sure.
Cool. All right. If people can't see and I need to explain things more thoroughly, I'd be happy to do so. But basically, I've trained it on neural network, and what you can see now is, remember we had a random surface that looked like this, and then after we train it, a very small network, you can see that the surface has morphed to fit the points, right? And this is typically what it means for a neural network to learn, right? In this particular case, for regression. And unfortunately, it's a little darker and smaller, so you can't see, but it hasn't fit all the points perfectly, right? Some of them are slightly above the surface itself, but for the most part, it's an approximation, and you can get arbitrarily close if you'd like. Now, what's interesting is that what I want to show in the next slide is, okay, this is on the training data, but how does this, let's call it a surrogate for now, perform on the rest of the space that we saw earlier? So we're going to overlap the two, and what you'll see is that it doesn't do too hot, right? And this is kind of like the first kind of lesson when it comes to training surrogates, which is that it's very much a data-driven process. So you're only going to get as good as the data that you have, right? And a lot of times when you deal with neural networks, and if you look into the literature, you'll see a lot of people try and get away with more model complexity and less data, right? And 9.9 times out of 10, this is something you should not be doing. Data is a first-class citizen in these kinds of algorithms. So it's very, very important to matter about this. And what I'm going to show in the next slide is that I'm going to increase the complexity of my network. So it's going to be, instead of 8 layers in the first, 8 units in the first, it's going to be like 32. And what you can see, unfortunately, it's a little dark, but the surface is more complicated, right? If you add more model complexity, like I was showing in the animation earlier, you have more kind of grid points to kind of fit your surface, right? Yes. More nodes. So when I come back to the first, yes, this one had 8, and then this one had 32. And you can see that, unfortunately, black on black and the screen being small, you can't see it. Well, if you look closely, you will see it. But not only did it fit the points much better, but if you look closely, there's a bunch of more complicated ridges. So it has more ability to express and represent the data. But if we go to the next slide and look very closely, you'll see that if I overlap it with the original surface, it still didn't solve the problem, right? It still didn't learn the actual underlying manifold. And the reason why this is very important is because, again, driving the point home, model complexity is important, but it is not a first-class citizen when it comes to these kinds of algorithms. Data is much, much more important. And the idea here is that these networks, if you think about it, based on what we've seen so far, they cannot do anything more than interpolate. So in this particular case, if you looked at the data that we sampled earlier, there are regions here that there was no data for. And you can see that the network just kind of guesses. And what I mean by kind of guesses is it just evaluates the points based on the weights that it has, and you can see that where the data was, the weights give a good answer, but where the data wasn't, it doesn't give a good answer at all. So how do you solve this? And really, this is such a simple point to drive home, but as an expert in this field, I cannot tell you how many times I've seen the complete opposite, which is people trying to kind of nudge around model complexity instead of dealing with the data. So what we're going to do now is more densely sample the surface, right? So you can see here that the data itself closely resembles the original manifold, right? And when I go ahead and train that same small network earlier that we had before, and I overlap it with the surface, you can see that even a small neural network can give you a useful answer. And I want to pause here for a moment because there's a very important point that I'd like to make, which is that in the world of surrogates, a lot of people have this notion that I need to train a model that's incredibly accurate because it needs to represent the model that I'm replacing. But there's a fine line between what is accurate and what is useful. And this is very, very important. And the reason why I want to drive this point home is that you can see that if I took this surrogate, if I took this model, and I did some kind of optimization, I wanted to find the maximum, I wanted to find the minimum, something like that. You can see that with this particular model, even the smaller version learned the topology correctly, right? Where the minimum is and where the maximum is. So if I use this model in an optimization routine, it'll still give me a very useful answer, despite the fact that the surrogate is not entirely accurate. And this is really important because most of the times when people want to use surrogates, they're taking a model, they'd like to do some kind of downstream optimization process. And in most people's minds, this model needs to be accurate in order for this optimization process to be useful. No. It needs to be accurate in the sense of it learning where all the humps and learning the overall topology, but if it was off in terms of error, you can still get a very useful answer. And later on, there's going to be slides that will kind of drive this point home a little more. Yes? So this is a fair point, and I'd like to answer that question a couple of slides later, because I'm actually going to show a model that's relevant to the domain to kind of drive this point home a little more. Yes. Mm-hmm. 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 Yeah, this is a clever way of doing uncertainty measurement. So that's a clever way of doing it. But in general, for the class of problems that we're talking about here, we assume we have a simulator. So this notion of data being scarce and not uniformly distributed is not much of a problem because it's free to just query the simulator and get uniform data. Yeah. Yes? Mm-hmm. Precisely. Yeah. So I mean, with neural networks, if you just use a normal deterministic forward pass, there are several ways to get an uncertainty measurement. One of them is using dropout. So you're dropping out your weights randomly, and you look at the variance, and then from there you get a sense of the uncertainty. Another way is instead of learning the mapping directly, you learn the mean and standard deviation of a distribution, and then the mean and the variance of a distribution. So your output is not the thing you're fitting, but it's the mean and the variance of it, and then that actually gives you a sense of uncertainty as well. So there's two ways to kind of take a deterministic neural network and be able to get that notion of uncertainty. You can also do a Bayesian neural network as well. There's many different variations to get uncertainty. Yeah. Does that answer the question? Oh. Okay, cool. So this is just a small network. You can see it's useful. It's not accurate. I mean, extremely accurate, but it's useful. If I did a maximum or minimum kind of optimization routine, it will find those points for you, right? And the key thing here that I want to mention is that you won't use the surrogate after you get those points, right? When you use the surrogate to get the optimization, when you use the surrogate in the optimization routine to get the points, you won't use the answer of the surrogate. What you do is you'll take the parameters that the surrogate learned and plug it into your original simulator, and then double check your answer. So the key thing here about surrogates is that these workflows are meant to augment your workflow. It's not meant to replace it. And I'll be highlighting this point much more later on. And this is very important as well because as scientists and as engineers, we have concerns about whether or not something will give us an answer with certainty, right? And so the key thing here is finding the right balance in using these algorithms so that we can walk away with the confidence that we would expect as if we were using our original model. So I'm going to show the next slide, which is the more complicated version of the neural network. And you can see that there's literally and virtually no distinction between the original surface and the model, right? And what this highlights is that representation complexity is important. The number of nodes, the ability for the network to learn, it's very important. But if you don't have data, it's not as important at all. But when you do have that data, then you start getting to these regimes where you can get that accuracy that you'd like, right? And so to kind of drive the point home here, the signal representing the surface is more important than the architecture trying to represent it. With the caveat, because this is not a general statement in the sense that you just forget about representation power. It's very important to have representation power. But the way I want everyone here to think about surrogates when it comes to working with them is that data is a first-class citizen, especially when you have a simulator. If you're not getting the accuracy that you want, you shouldn't be trying to tweak much on the complexity side. You should try and get as much data. And only when you get a certain threshold of data and you don't start meeting certain kind of metrics or requirements, then start playing with your complexity. But it should be data first and then model complexity. Any questions so far? I think we've had a lot so far. Okay, so this is a very quick kind of a nerdy moment, but I strongly suggest everyone in this room, if they've ever had the chance, to read this essay by Richard Sun called The Bitter Lesson, which will kind of give you an intuition about how to think about these algorithms in the future. And this was written in 2019, and everything he's written so far has come true. And the idea here basically is that for the longest time, ever since artificial intelligence was applied to even things as simple as games, you had a whole network of researchers that would try and kind of hand-tune a solution and add human abstractions and things of that nature. But then what ends up happening is more compute becomes available. You just use these generic learning algorithms, and they end up performing much better by a large margin. And it's called the bitter lesson because we keep kind of repeating the mistake every single time AI gets implemented into a new domain. We kind of go through the same cycle. We start adding human abstractions and trying to get away with less data, and then afterwards, we just have much more compute that comes available next year, and then you can use learning and search, and you end up solving the problem anyways. And that's kind of the point. There's there can be some discussion points about whether or not we fully agree on the premise, but I think it's a very important kind of starting point for most people to kind of get the right mental model when it comes to working with these algorithms. Okay, so I'm going to briefly go through the kind of different types of deep learning surrogates, and then we're going to walk through an actual example. So there's many different neural network architectures. I just want to put that out there. This is not necessarily about architecture, but more about different kinds of scenarios that might be relevant for the folks here that are at the conference. So in particular, there are 3 kinds that I have here, and I'll kind of walk through different examples for each one. So in the first case, you have a discrete time surrogate. This is like doing a dynamical model that's discrete. So you're doing time stepping at each time point, and you can think of the inputs being your state, your initial condition, your parameters. If it's non-autonomous, maybe include time, a forcing function, and then the next output is the state at the next time step. And then you have a continuous version of this, which is the architecture in the middle. And then there's the final one, which we'll see a form of in the hackathon and also through a walkthrough example today, which is that an example would be you have a jet engine, you have a series of parameters, and then you have a steady state model for it. So you plug in your parameters, and then the output is some kind of steady state value. It's just a single vector or a scalar or whatever it is. And so these are the kind of 3 most relevant kind of, I would say, mappings and not architectures for the world of scientists and engineers. Of course. Yep, forcing functions, yep. So that's part of the input as well. So the input would be the state, the parameters, if it's non-autonomous, time, and also your input functions. And then the output would just be the state. Exactly, exactly. And that's the way to think about it. There's nothing special about adding forcing functions or parameters to your neural network. It's just literally another bunch of set of inputs that you just add through and train. Okay. So now this is where I want to talk about the source of speed, because a lot of times when people work with surrogates, it's for some reason how fast these things can actually be, the kind of speed ups they can give you, is not easily understood. So I want to walk through this very quickly so that people can understand how much throughput you can actually get with a surrogate, and it really is a lot. So the first source of speed that you get from a surrogate is the forward pass, and what I mean by that is you plug in inputs, you get your outputs. Neural networks are based on very parallelizable units of compute. You can run them on the GPU. And so a single forward pass, a single simulation of whatever you're interested, is going to be tens or thousands of times faster than your original simulation, especially if your simulation's in the order of even seconds or tens of seconds, because a forward pass of a neural network, of a relatively large neural network, can be anywhere between in the microseconds to milliseconds on the GPU. So it's going to be much, much, much faster. And that's one simulation at a time. And the key thing that I want to point out here is that because of the nature of the architecture with the matrix multiplications and whatnot, you can do multiple evaluations simultaneously. Right? This is the kind of batch evaluation process, right? So your source of speed is twofold. Not only is a single simulation faster, but you can do many simulations in parallel as well, right? And that really increases your throughput. Oftentimes when we work with customers and we get into the situation of explaining, oh, your circuit is 100 or 1,000 times faster, it's very hard to understand the nature of that speed up. Because we're talking about 1,000x means that if something took you a year, to finish, in terms of simulation, whatever it is, with 1,000x speed up, you're not even looking at a day, right? So in terms of the kind of paradigms that get unlocked with this throughput, it's very hard to understate. It's very hard to understate. And so does this make sense for everyone in terms of how we get speed from the neural network? With a single evaluation being very quickly with matrix multiplications, and then you can do batches, you can do multiple at the same time. Is that clear? Okay. Of course. Yes. So in the case of a time series where you have to predict the next time step every single time, and you have, let's say, 10 or 12 time steps, you're going to have to still repeat your evaluation. But the point is that single evaluation will be much, much, much quicker. Yeah, it's a good question. Any others? Okay, so now what I like to do is kind of go through the process of helping people understand and giving them a mental model of when we should be using these classes of algorithms and when we shouldn't, okay? So you can see that there's a common theme in where the check mark is, right? When you have a simulator, when you have a lot of data, you're in a good position. Now, sometimes you can be in the position where your simulator is not differentiable, okay? Your simulator is not differentiable, and it's not fast. This is a perfect situation for a surrogate. The reason why you want it to be differentiable is because once it is, it becomes incredibly useful during optimization. And I will be showing that later on, actually, right? So that's one scenario, where a big check mark. Now, if your simulator is fast but not differentiable, also a very interesting case for a surrogate, right? Now, the question mark case is one I'd like to kind of dive into a little bit because it's kind of common in a lot of domains where you have little data, and I want to be very clear here. When I say little data, I mean real world data. I don't mean simulator data. So here you can see I make a distinction between data and simulation or simulator if you have access to a simulator. So the first two are just based on simulators. But suppose you had real data and you had a semi-accurate simulator. Should you build a surrogate? And it all depends, right? If your simulator is slow and the semi-accurate simulator gives you useful results, then yes, you can build a surrogate. But if it's not there yet, then you have actually a step just before generating a surrogate, which is called model discovery. This process of trying to complete your equations and get more accuracy in your simulator. And once you do that, once you have a more accurate simulator, then you can start querying it and generating a surrogate. So it's kind of like a twofold process. And this is this part of model discovery and scientific machine learning. This is where Chris' presentation will be coming in. But I just want to kind of comment about this particular scenario that it is oftentimes people will, if you have a semi-accurate simulator but it's not as useful as you'd like, you don't want to actually start building a surrogate. You want to take the time to actually do some kind of model discovery, correct your equations, find something more accurate, and then start querying it in a way that you would to generate your surrogate. Yeah, precisely. Precisely. You have a climate model, and then maybe you have some data from buoys in the ocean or whatever it is, and then. Precisely. Precisely. Yes. Very good question. So does everyone have a good intuition of some hard and fast rules for when we should dive deep into these things and when we shouldn't? Okay, cool. Okay, so now we're going to the process of how to generate and build them. So it's a pretty simple process to generate and build them. It's just a typical machine learning workflow, but there are different parts of the pipeline that are not easy to get right the first time if you're not an expert. And those are the particular parts that I'd like to kind of dive deep into and make sure that we kind of have a thorough understanding. So this is just the high-level workflow of what it looks like. You start off with an input space. So an example would be, I'll be giving an example later on, but some kind of input space, you sample. Each sample you simulate, then you have a whole bunch of simulations. You pre-process it, which means splitting it, normalizing it. You know, these are like technical details when it comes to training. I'm not gonna go too deep into that, but there are some pre-processing workflows that you have to kind of put the data through to massage it and prepare it for training, so that training converges well and quickly and is well behaved. And then once you train it, you validate it. And if it doesn't meet spec, suppose you start off with, okay, I need this thing to, when I use it, I need it to give me a very useful optimization answer. And you can define what useful means. Or it could be an accuracy metric. I need this thing to be 0.1% relative error or something like that, right? And you validate it. And if it doesn't do what you wanted it to do, then you have to close the loop and start resampling to increase the performance of the surrogate to get it to where you need to be. And remember, we talked about earlier how neural networks have this special property of universal function approximation, a theorem that allows you to get any kind of arbitrary accuracy that you like. So you have a nice guarantee there, but you really do have to work with it in order to get there, right? And the resampling part in practice is really called active learning, for those who are familiar with that term. And there's many different algorithms to do resampling really well. It's actually one of the parts. I would say it's after generating your first stack of data, it's probably one of the most important parts of the entire surrogate process in order for you to get the kind of accuracy that you want. Okay? Any questions about the high-level workflow? Yes. So neural operators are classes of algorithms. It's a kind of architecture. It's not a high-level machine learning workflow to generate a surrogate. It would be one of the three kind of, it would be the last architecture that I showed back here. So let me just go back here very quickly. it would be this one on the right here, where it's a forward pass. So an example of a neural operator is like you have a dynamical system, and instead of learning the differential equation itself, you learn the solution, right? And in that particular case, you still need the same process. You still need to sample data and make sure it performs well. It's just an architecture thing. It's not an actual workflow. Yeah, these are good questions. Anything else? Cool. Okay, so I'm going to be using the kind of Rainmaker simulation just because I fell in love with the whole thing. You know, big shout out to Miles for working on it and doing such a good job. And I'd like to use it because I feel like it's such a relevant example for everyone to understand. And we're gonna kind of go through the most important points step by step. So, unfortunately the screen is small so you can't see, but you can see that the simulator has a bunch of parameters of interest, right? So I think I can read it out for you here. It has the orography scale, the mountain height, you know, mountain size, mountain longitude, latitude, temperature of the equator, temperature of the pole, temperature of the Atlantic, temperature of Azores, the zonal wind, and then you see that there are numbers, bounds beside them. This is a very important process because when you sample, you need an upper bound and lower bound. And typically speaking, when you use a model, as a domain expert, you know what region of interest, broadly speaking, that you'd like to use the surrogate in. So you have to define these kind of upper and lower bounds to begin with, right? Then the next process is you sample. There's many different algorithms to sample. A great package to use is quasi-montecarlo.jl. And there's all kinds of algorithms that allow you to sample. I think for the example that we use here, we use the Latin hypercube algorithm to sample, right? And when you're done, you simulate. And the really key thing here is that it's a very intensive process. So simulation requires a lot of good infrastructure, right? You need distributed compute, depending on what kind of model you're using. If it's using GPUs or whatever, it's a very infrastructure intense process. And typically trying to do this on your own is going to require you to kind of, you know, dip your feet a little deep into distributed computing and the world of GPUs and everything else. So, you know, fair warning in terms of this part. It seems simple on the slides, but when you get into the actual details, you know, you would much rather having an expert kind of do it for you than kind of doing it yourself, if you had the option. But it's still relatively simple in the sense that you pick your relevant parameters of interest. And I want to pause here for a second because popular, a kind of misconception is that if you have let's say for example, your original parameter space was 1,000 parameters, right? But you're only interested in like 4 or 5 when you vary them, right? You shouldn't build a surrogate with 1,000 parameters. You should only build a surrogate with the 4 parameters of interest, right? And most people would think that, oh, but it's partially observable. There's not all the data is available to model the problem. Again, you're kind of thinking too much on behalf of like the neural network and its ability to learn these kind of representations, right? So just kind of pull away from that complexity. Don't worry too much about that. Instead, phrase your problem as simple as possible and as clear as possible for exactly how you want to do it and move forward. There are subtleties to this, but this is kind of like a general rule of thumb. You don't need the entire parameter space. You only need the ones that you're interested in, right? That's the bottom line of it. Okay, so this. Indeed. First and foremost, it reduces the dimensionality. And so the number of samples required to cover your space densely enough in order for you to have a neural network to interpolate is going to be much, much, much larger. Now, of course, there's the manifold hypothesis, blah, 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 that says that, you know, in the space of high dimensions, there exists a manifold of a lower dimension that actually represents your data, so you actually don't need that much samples. But, you know, we're not going to roll the dice here. And instead, you know, just be practical and pick your actual set of parameters rather than go for the whole thing. Yeah, this is a good question. Certainly. So this is usually a domain expert thing. So, for example, it's really based on how you use the surrogate. If you, for example, if there's a set of parameters that you think that are most important to find or tune, then those are the ones you use. Yeah, it's like a subset in that sense. Okay, beautiful. So what I'm showing here is, you know, what happens when we try and train a network. So we take our examples, we pass it through, so you can see it goes through the network. Forward, we go to our objective, which is, you know, if this is regression, so we're doing point fitting, so this is your mean absolute error, your mean squared error, yada, yada, yada. And you can take in your ground truth, you find how much you're off, and then you backpropagate. You go through the weights and you update each one, so the next forward pass that you do will be much closer to the answer. And if you do this enough times over and over and over, you'll see that your loss or your curve of accuracy is going to go down close to 0. So this is like the very basic, broad idea of how these things actually learn. If you're not familiar with backpropagation and all those algorithms, you don't have to worry about it. The general idea at a very high level view is you pass your data through, you have some kind of objective, and then you calculate a change that you need to add to each of those weights, which are those lines that you see. And the different colors and the different thickness represents how large or small those weights, how important they are, and how not important they are. And over time, the network will tune using the gradient and give you a set of weights that will give you something that will approximate your function. That's really how it works. It's very simple. It's very straightforward. And this is a very important property, the fact that you can backpropagate through when you do downstream optimization. I'll be showing this later on. But this is kind of like the very basic overview for those who haven't been introduced in a prior sense to how a network learns in a very kind of high-level visual sense. Does that make sense for everybody? Okay. So once you're done training your circuit, the fun part is validating it. How well did it do? And there's many ways to do this, but I'd like to show one very effective way, which you'll see in the hackathon, which is called the parallel coordinate plot. Just a show of hands, how many people have actually seen a parallel coordinate plot before? Ugh, of course, Chris and Miles. Okay, cool. So I'm gonna take the time to actually read this out to you, because when you see how it works, you'll realize how useful it is. Okay? So you have a set of vertical axes. You can see that there's 5 of them, right? The first 4 are parameters. Those were the inputs to the model, and the last one is error. Okay? And each line that passes through an axis represents a sample and its corresponding error point. Does that make sense to everybody? Right? And so I know, I'm so sorry. I wish. Yeah. Oh. Okay, now we get to see, now this gets beautiful. I swear the animations were even more beautiful before, but hey, you know, we take what we get. So, again, you can see one line traces, it'll be a sample of a parameter that you took, and then the corresponding error. And the cool thing about this plot is that just by looking at it, you can see at a very high level view across your entire parameter space, where's the surrogate doing poorly and where's it not. And you can actually slide over these axes and select which line, so you can actually explore the space as meticulously as you'd like. So you can see, just from the starting point, I wish I can pause this GIF. But you can, I should probably stay beside the microphone. Too much of a active person here, apologies. But you can see that the highest error is actually at the extremes. And this is usually typically the case because when you sample, when you use these algorithms that are, when you use these sampling algorithms that are designed to sample space as densely as possible, it's really good at filling space, but when you get to these edges, it doesn't actually sample those places as much. So you can actually see, I mean, you can't see it now, but right here, that the lighter colors are the higher error, and you can see a very clear pattern. Certainly. So the first 4 axes are your parameters. So remember how we had our input vectors earlier here? Those would be your inputs. So here there's 5 here, but in this parallel coordinate plot, there's 4, okay? And the final axis, it says error. I'm so sorry you can't see it, but it says error. So one line, just trace one line. Pick any line that goes through the first 4 axes, and that will be a sample that you took from before. And then where it ends on the last axis is the error of that sample when it was passed through the surrogate. So how well it did. Yes? No. This is all kind of pre-computed ahead of time and just lets you kind of visualize things. Yeah. But the point is that the sliders let you pick different parts of the parameter space and then view the error. Sure. Because, yeah, I can't leave the microphone. I'm sorry. Yeah. Oh, it does? It doesn't. It won't let me. It's a GIF, unfortunately. Yeah, I should have done a video.
Right here, where do you think that most of your error is going to be? If you look at this, when parameter 4 is very high, this is when you have all of the lightest, it's gone now. But yeah, that's where you have all the highest error
course. No, not the networks. So remember, the example is we have a surrogate. It's like a dynamical system that has different parameters. So these parameters are not for the neural network. It's for your simulation. It's the surrogate that's representing the simulation. So just like you take a bunch of parameters into your simulator, maybe an initial condition, and you simulate it and you get a result, for the surrogate, you take the same set of parameters, you pass it through, you get your simulation. Yeah, yeah, yeah. Yes. Yep.
And then what this would be telling you is like, oh, when the mountain height is very high, that's where the surrogate model has the least accuracy, right? That's when you can trust it the least, right? And so, and then it says, oh, on average, you can always trust that the surrogate's within 5% error, but when the mountain height is high, then that's when it's kind of at the 5% level. When the mountain height is low, then it's kind of more has about a 1%. Right? That's the kind of thing that you're able to do.
Nathaniel. Yes, the surrogate minus the original simulation. Yeah, yeah. Yep. Sure, sure. So I'll explain the process. It's a great question, right? So the way you generate your parallel coordinate plots, you take all your training data after the surrogate is trained, you make your predictions on each sample, you find the error, and then you plot. So it'll take each of the samples that went in, that was an input, and then the corresponding error. And then the bottom is the actual simulation. You can see the bottom there is the actual simulation of the curve. You can see that it's almost line over line, and there's a histogram of error just on top of it there. So you can see that it shows the simulation there, right? So the top is the parameters. You plug in a parameter, you get a corresponding error. It's just all scalars so that it can be visualized. And then the actual time series simulation, this is for a dynamical system, you can see is at the bottom, and it's basically line over line. Is that clear? I love these questions, by the way, so I'm glad everyone's into it. Of course. Yep, yep. So every training example you pass in, you get an error. So you do that over and over and over, then you get a whole bunch of errors for each training example, and then you just create this plot, where for each training example, which is one line, this is the error that you got. And then you can view the actual curve that the surrogate predicted at the bottom. Yeah, yeah, this is fair. So usually what you'd have to do is, if you see there's like a checkbox over there that allows you to kind of check what you can see. It's at the right corner over there. Sorry, left corner. And so you can turn off and on the states of interest so you don't visualize all of them at once. But yes, if you have a large state vector, it's a lot of bookkeeping, that's for sure. And it's a visualization challenge. But there are ways around it with the parallel coordinate plot. Okay. So what I want to do now is I really want to talk about the exciting part, right? Which is actually using the surrogate. And this is the part that I'm most excited about to kind of walk through with everyone here, because this is where you start seeing the true power of this actual algorithm, okay? So I'm going to walk through this step by step. Please stop me if you have any questions, but it's very straightforward. So earlier, if you remember, I showed you a very similar diagram that was about training, right? So I take a bunch of inputs in, I do an objective, and I update the weights of my network, right? And then when I'm done, I have a trained neural network. Now, in this scenario, I am not updating the weights of my network. Instead, I'm doing an optimization problem. So an example is, in the hackathon, you guys are going to be doing, for the Rainmaker, you'll be finding a set of parameters that will maximize the total precipitation. So you can think of the objective here as maximize my total precipitation. So I plug in my parameters earlier, which was the mountain latitude, longitude, the temperatures, et cetera, and I just randomly sample from the space a bunch of samples in. So the initial guess 1, initial guess 2, initial guess 3 is just me taking a random sample from that space, okay? I pass it through my network. I compute the objective, so how much maximum precipitation does this sample give me? And then because it's differentiable, I can walk back through the network and update the initial guess. Do you see this, right? And the most beautiful part is that I don't just have to do this for one sample. I can do this for many samples. And the reason why this is important is because in optimization, when you're dealing with a non-convex scenario, it's very easy to run into local minima, right? So you can see, for example, one initial guess up there. When I optimize, it didn't really go anywhere, right? But if you see for the other guesses, it was able to find the minima. This is the minimum, not the maximum in the previous example, right? But you see how the usefulness of the algorithm is that when I can batch, I can do many guesses across this manifold. And then I can do an optimization procedure that will find either a max or min, depending on where your objective is. And I can actually do this all in batch. So it is very, very, very fast, right? And it's like, you can think of how expensive, global optimization routines are when they don't use gradients. And this is almost like a surrogate version of a global optimization procedure, where you get to have many initial guesses, many different starts in your parameter space, and then through gradient descent, you can find the actual maximum. And it's very, very fast, right? And there's a very cool paper that Chris published very recently that takes this technique to the next level, where instead of just taking random initial guesses, what if you went a little further and take the best that you learned and then resample again and get even closer, right? Using particle swarm and whatnot. So that's an example. Do these two slides make sense for people in terms of the optimization? I think this is a very critical part because this allows you to see why it's useful to have a surrogate that's differentiable. Okay. I can't see anymore because it's pretty dark, so I'm assuming people are nodding their heads. Okay, and now this is just me kind of showing off the results. I didn't plot these results. It was actually Miles who plotted it. But I just wanted to walk through. I'm not going to spoil too much because I don't want to say anything about the hackathon in terms of like what we actually get. But there was a bit of a competition at yesterday's dinner in terms of who could build the best output result. And I took that a bit personally, so I decided to add a few slides just to kind of put the haters in their place there, just to explain the nature and outcome of this surrogate. So the Rainmaker challenge is a very beautiful challenge. You get a whole bunch of parameters. You learn how to maximize your precipitation. And in this particular example, the surrogate that was trained was not accurate. It did very well on training. On validation, it did kind of okay, right? But this is where I was talking about the difference between useful and accurate, okay? The surrogate was not accurate in terms of regressing, given a parameter, here's the total accumulated rain. It didn't get the exact accumulated rain, but it learned the underlying behavior of the actual data well enough that when I did optimization on top of it using the technique that I showed you earlier, it was able to get a very good answer. Now I want to explain the context of this answer because yesterday I said 220 milliliters of rain. I was like, oh, that's so easy, et cetera, et cetera. But the interesting part is if you take the simulator and the bounds that were specified and you sample 10,000 times, that's what your distribution looks like. You can see it's very heavy-tailed. And if you do some statistics on top of it, you'd realize that getting 229 milliliters of rain is very unlikely in this space. Yes. Yes. So if you didn't have bounds on your parameters, I'm sure you could have had fun and created any unrealistic scenario. But there were bounds on the parameters. And within those bounds, you can see that the surrogate's output was 252 millimeters, which is not obviously 229. But when I took the surrogate's prediction in terms of the parameters that I showed you earlier, remember these initial guesses that we were learning? I took the best one and I plugged it into the original simulator, not the surrogate, because you want the real answer. You don't want the surrogate. The point was that if I used the original simulator, if it wasn't differentiable, I wouldn't be able to do this. And furthermore, if it was very expensive to run, it'd be very, very slow to find the answer. So a very useful way to use a surrogate is explore your space quickly, get a useful thing, explore that space quickly, find a sub-region of interest, and then go ahead and use your original model if you'd like, right? Augment your workflow. You don't have to replace it. But this is a very important distinction between useful and accurate, right? And a lot of times, what's preventing people from going ahead and using these techniques is they're so set on accuracy. But you need to understand that there's a large margin of value that can be gained if you just kind of take the perspective of, I need something useful as a starting point. Kind of like a warm start to an algorithm. Does that make sense? Please. Sorry. Yep. Yeah, certainly. Because this is all positive, another example that will get it to a normal distribution would logging it, right? So that'd be very simple. It will actually take it to a log distribution. These are the pre-processing techniques that I was talking about earlier in the beginning of the pipeline when you take your data and if you want to massage it. But actually, instead of trying to just massage your data to be uniform or normal, what you can do instead is you can do active learning. So you can find the parameter spaces that are less sampled and usually those are the parts that the surrogate will do the worst on. and then you resample those spaces so that you can actually even it out instead of trying to pre-process and get away with the lack of uniform distribution. Uh-huh. Oh, by making it convex, like the optimization problem? I don't think that's trivial to do in the neural network case, because in the end, I mean, you could get clever with your objective and trying to make it convex and everything else, but yeah, this is what I thought you were talking about was since this is not a uniform distribution. If you train a surrogate on, it'll be much more complicated to do very well because you kind of have a lot of points representing one part of your predictions, but not a lot on the other because it's heavy-tailed. So what you want to do in this situation is you want to just balance everything out. That's what I thought you were talking about. But yeah, making it convex is a little more, I think it's very, very non-trivial. But I think I'm running out of time, unfortunately. I had a whole bunch of examples here that showed real-world examples that we do at JuliaEO of different kinds of surrogates that are very, very complicated, very difficult to do. I don't have much examples, so here's some eye candy of an F1 car and an actual battery model and things like that. But I think I'm going to end here. And I'm very excited to work with everyone here. I'm looking to collaborate and help anyone that has a very hard problem that they want to apply machine learning to. Come talk to me, and thank you so much.
Yeah, I hate interrupting this conversation.
No, I'm so sorry. I just kept going.
No. It's fine. That's the interesting bit, I think. So the presentation you make is kind of the past already, right? So it exists, and these discussions are what creates new stuff. So what we could do, if you have quite a few more slides, and after lunch we could create a small session, and you can continue the discussion.
Sure.
But let's not delay the calendar as well, the program, because we have people online. So let's have our coffee break. Also, great news for those who are interested in this topic is that on Friday there will be a hackathon about creating a surrogate model. So keep an eye on the program. I'm changing it today. Slight change is just Friday. So this doesn't apply if you are online, but Friday's afternoon hackathon is going to be moved to the morning, and we're creating a brand new hackathon in the afternoon because it turns out that Alex has a great data set that people want to explore, if I understood correct. So we can try that. Yeah. Okay, so meet you, we'll restart instead of 5 past at 10 past, if you are online.